Welcome to a course in real analysis. This is lesson 1 discussing the group axioms. Now, to give a quick summary of everything that's going to be contained in this video, we will see the definition of an identity element, inverse element, examples and exercises that try to gesture at the variety of things that a group can be. In particular, most of the examples will be numeric, but at least one will be non-numeric. So first of all, just to give you a big picture of what I am trying to do here, I'm going to tell you what a group is. But why am I going to tell you what a group is? Well, it is so that I can then state as an axiom of the real numbers that the real numbers form a group. Now, to get started with stating what an identity element is, let's consider any non-empty set. We're going to write that as X. And we're also going to consider an operation on X. Now, even right here, let's just pause and appreciate what it means to say that star is an operation on X. So an operation is a certain kind of a function. And here we're talking about a binary operation. Throughout these videos, I'm typically going to just say operation, and implicitly it will be a binary operation. But here's what that means. The domain is going to be X cross X. That's the set of all pairs of elements from X. Now, already what you should be imagining is how this lines up with notions that you already have from the real numbers. In particular, let's start by talking about the plus operation on the real numbers. So imagine that X is the real numbers, and imagine that the star operation is the plus operation. How does that operation work? Well, you have to give it two real numbers. That's why the domain is X cross X, or if we're particularly talking about the real numbers, then that would be R cross R. But that's the domain of a binary operation, is this set cross itself, representing that you give it two elements from that set. Just like with plus on the real numbers, you give it, right, you can add two real numbers together. And then what is the output of that function? Well, when you add two real numbers, you get a real number. And that also is part of what it means to be an operation, is that when you give it two elements from X, it returns back out a single element from that same X. So let's also just keep in mind that we're not only going to have star be the plus operation on the real numbers, we'll also consider star as sometimes being the multiplication operation on the real numbers. So again, think about how that works as a binary operation. You give it some two real numbers, and it returns back out another real number. So that's the notion of an operation. If I tell you that something is an operation, it means that the domain is X cross X and the range is X. That's an operation on X. But okay, let's now get back to saying what an identity element is. So suppose that the set X has this element E, which is what we traditionally write for an identity element, especially in this abstract setting where we don't know what the set is and we don't know what the operation is. Then that's an abstract setting, right? X and star could be anything as far as we know. And in this abstract setting, we typically write the identity element as E. But again, as you go through this, keep thinking about how this lines up with how you know it's going to eventually be applied, which is with X being the real numbers and star being, let's again start by talking about the plus operation. What's the identity element for the plus operation on the real numbers? Well, it's the number 0. And why is that? Well, in a very intuitive sense, 0 plus anything is just equal to that thing. You could say that when you add 0, you don't change the number. That's a way of thinking about why 0 is the identity element for addition on the real numbers. Now notice that if you change the operation, if we instead talk about multiplication on the real numbers, then the identity for multiplication is different. It's the number 1, because 1 times anything doesn't change that number, right? You just get that number back out at the end. So that makes 1 the identity for multiplication. Now, let's get back to this definition, where here we're in the abstract setting where we don't know what x is, we don't know what star is, and in general, for any x and star, what it is to be an identity element is that E star x equals x, right? That's E being the identity element, that it does not change x. And also, if you swapped it around, right, on the right-hand side of that centered equation, that's x star E, and that should also get you x. That's kind of like saying x plus 0 should also get you x. Or if we were talking about multiplication, that would be x times 1 also gets you x. So that is the behavior of an identity element, is that when you take the operation with any element, you don't change it, in a sense. But okay, let's move on next to the notion of an inverse element. So again, we're going to take x to be any non-empty set. We'll take star to be any operation on x. And notice that the first time I introduce something, like the star operation from before, I tend to be a little bit notation heavy, right? I tell you that the domain is x cross x and then it goes to x. As I tend to use things more and more, I don't belabor the point. I don't go into so much detail since we've already done it once before. So here, I'm just telling you that star is an operation without being explicit about the fact that that means its domain is x cross x and its range is x. But that's what you know, right? That's what I'm telling you when I say that we are assuming that star is an operation on x. So anyway, we will assume that x is non-empty, star is an operation on x, and we're going to assume that x has an identity element, which we're going to write as E. And with all of those components in place, we can now say what it is for some two elements to be inverses of each other. And again, as you go through this, always try to line up what we're saying here with what you know about real numbers and addition as well as multiplication. So what does it mean for two things to be additive inverses of each other? Well, it's for them to be negatives of each other. It's the idea that if you took these two things and add them together, you get the identity, which again, for addition, is the number 0. But also think about how things change if instead you took the operation to be multiplication. So for multiplication, you would want two things which multiply and result in the identity, which this time is the number 1. So here are some additive inverses, 1 and negative 1. Okay, how about negative 7 and 7? Those are additive inverses of each other. For any number, if you just take its negative, that's going to be its additive inverse in the real numbers. Now you should feel invited to pause the video and think about what the multiplicative inverse of the number 2 is. And I'll give you just a second to pause and think about it, but assuming that you've already done that, and now you're coming back, the multiplicative inverse of 2 is 1/2, because 2 times 1/2 is the identity for multiplication, which is 1. And now hopefully that consideration helps you to read this formal abstract definition, which says that if x and y, little x and y, are two elements of your set big X, then if they have the following property, if they satisfy the following equation, that x star y equals E and also y star x also equals E, then in that case, we call x and y inverses of each other. Now let's have a brief word about notation. So typically when we're working in this abstract context with a set x and we don't know what x is, and an operation star, again, we don't know what that is, so that's abstract, then we tend to just use multiplication notation. And so you'll see here what I mean by that. Rather than writing x star y, we would just write xy, right? That looks like x multiplied by y. But what we really mean is just that in this abstract setting, it's just taking x and performing the operation with y. And also, when we talk about the inverses, right, say that we're talking about y being the inverse of x, just imagine that that's what's going on, and we want to express that, how do we write it? Well, we say y equals x to the negative 1. Now that makes it look like y is the multiplicative inverse, right? X to the negative 1, that's like the reciprocal, and that is what gets you the multiplicative inverse for any non-zero x. So that makes this notation look like it's talking about multiplication. Just know that when we write that, in the abstract setting, that's just kind of our traditional default notation, but it doesn't really mean that these have to be numbers that are being multiplied. But okay, with all of that now out of the way, we can finally state what it is to be a group. So let G be any, and here I should have said non-empty, but let G be a non-empty set. Now I am switching from typically using the letter X for my set to now using the letter G. That's just to be indicative of the fact that I know that this thing will be a group. But there is no like mathematical difference between using X or using G for the set. But in any case, so we have this operation on G, and we say that G is a group if the following conditions are all met. The star operation must be associative, and I'm assuming that the viewer knows what that means from a previous course in discrete mathematics. The operation must have an identity element as we defined it earlier. Again, when being abstract, we write it as. And the operation must have an inverse for every element of X. So if you take any X in G, its inverse, right, there must exist some other element also in G such that when you put them together in the operation, you get the identity. And there you have it. When any set and operation satisfy these conditions, we call it a group. Okay, let's exercise this new idea by looking at some examples and some non-examples of groups. We'll start here with the integers under addition. Now, before going much further, I want to point out something that I'm doing somewhat stylistically to help you to understand what's going on here. I'm typically writing the abstract representation of something on the left-hand side of the equal sign, and then its particular application in this example on the right-hand side. Now, there's no mathematical rule about this being how things need to be written. I'm just trying to sort of maintain that theme so that you can easily align, right? The thing on the left is abstract, the thing on the right is this particular application. So in this particular example, the abstract set is here being identified, particularly for this example, with the integers. If you look at the operation, abstractly we write that as star, but here, because I want to talk about addition, then that's what the operation is in this application. And so anyway, I am going to claim here that this is an example of a group. And so let's just kind of go down the list of all the things that you have to check in order to confirm that this is a group. Well, we do need to know that the set is a non-empty set. That's usually a trivial check, right? Because there's only one empty set. But anyway, the integers, non-empty set. Next, we need to check that the operation truly is an operation. And here, the plus function, if we want to call it that, is an operation on the integers. And you might think, well, isn't that just so trivial? Isn't that just always going to be true? Do we really have to check that? And the answer is no, which I will demonstrate by way of an example. So consider subtraction on the natural numbers, which may at first seem like it's an operation. I mean, it's so similar to addition. But then think about what you would have to say about, for instance, 1 minus 2. Now, what is that? If subtraction is supposed to be an operation on n, the natural numbers. Well, there are kind of two things that you could reasonably say about this example. You could say that 1 minus 2 is negative 1. But then if you did that, then this function, the minus function, would, yes, receive two natural numbers, but then output an integer, making the minus function not an operation. Now, you could perhaps try to approach this differently and say that actually we just won't define what 1 minus 2 is. That just won't be defined for our function. But if you did that, then now the domain of the function is no longer n cross n, and for that reason, it is not a function, or sorry, an operation. So no matter how you try to resolve this issue, you never get subtraction to be an operation on n. And all of this is done just to demonstrate to you that whenever you are handed some arbitrary set and a function, even if it seems like it is an operation on the set, you must truly check it because sometimes you can be surprised. You really have to check that the domain is x cross x, whatever x is, and that the range is also x. But okay, let's return to the example that we started with, the integers and addition. And now I've made my case that although the plus operation truly is an operation, that is something worth thinking about and checking, but we're done with that now. Now, the plus operation on integers is associative. There is a proof of this, but that's not the kind of thing that we're interested in our class, so we'll just accept and take it for granted that plus on the integers is an associative operation. Next, we check that this has an identity element. Of course, we already saw that 0 is the identity for addition for real numbers, but that's just as true for the integers. It's completely obvious. Next, we check that every element has an inverse, and so for any given integer, it's negative, or multiplying by -1, is the additive inverse. So yes, every element of this set with this operation has an inverse. And that is it. That is the confirmation that this is an example of a group. Now, next let's look at a non-example, an example of something that is not a group. And here we're going to take the natural numbers with addition, and it may be surprising to learn that this is not a group, perhaps. So let's check all the conditions one by one. Is the set non-empty? Yes, it is. The natural numbers are non-empty. Is this function truly an operation? Well, yes, if you add two natural numbers together, you get a natural number. What about an identity element? Well, at least for the moment, let's just assume that the natural numbers have 0. You know, some authors say that the natural numbers does not have 0. Some say that it does. Well, let's just assume that it has 0, and therefore it has an additive identity. And finally, let's consider inverses. Well, if I'm saying that this is not an example of a group, then since it passed all the earlier tests, then this must be the one that it fails. And yes, indeed, the additive inverse of 1 is -1, but that is not in the set of natural numbers, so this does not have additive inverses. And that's why this is a non-example of a group. Okay, let's move on to another. And here we'll take the rational numbers with the operation multiplication. And this is a non-empty set. The function is an operation. Multiplication is an operation. It is associative, right? Multiplication of rational numbers is an associative operation. What about the identity element? Well, recall that what that means is that we need to find some element, for now we'll call it E, such that for every other element, E times B, in this case, is equal to B. So we've already said that the identity for the real numbers is the number 1, and I think pretty obviously that's going to be the identity here as well. But go ahead, confirm it for yourself and see that, we know that 1 times b is equal to b for every rational number b. So this does have an identity element. So again, as before, if there's going to be an issue since it passed all the earlier tests, the problem must come with inverses. And indeed, if you think about most numbers like 2 and 1/17 and whatever other rational numbers you want to think about, they each have inverses. Most rational numbers do have a multiplicative inverse. The inverse of 2 is a half. The inverse of 1/17 is 17. But there is one number which does not have any inverse, and that's the number 0. And if that's at all confusing, think about what it would have to mean for 0 to have an inverse. It would have to mean that there is some number, call it b, such that 0 times b equals 1. And it does have to equal 1 because that's what we said was the multiplicative identity. And so, since we know that that simply cannot exist because 0 times anything is 0 and not 1, then therefore 0 has no inverse, and this cannot be an example of a group. But this might make you think, well, that seems a little unfair. I mean, Q is so close, right? The rationals with multiplication is so close to being a group. It's just for that one number 0 that makes it not have inverses. Couldn't we just delete 0 from Q and obtain a group that way? And the answer is absolutely you could. So if you did take Q, remove 0, that is now still a non-empty set because we didn't remove everything. It still has an operation when you restrict multiplication to the now appropriately smaller set Q minus 0, then that is an operation because if you take any two numbers that are non-zero and you multiply them together, you don't get 0. So actually by removing 0, we still have an operation on Q minus 0. So that's worth noting, and it worked out. But anyway, so going through the check of all the other properties, this does result in an associative operation, right? Removing 0 does not change the fact that everything else continues to be associative. It still has an identity because we didn't remove 1, and 1 was the multiplicative identity. And now, by construction, by the design of removing 0, everything now has an inverse. And so yes, when you remove 0, now this does become a group. Okay, now I'm going to give one more example, and the point of this example is just so that you don't come away from this thinking that all groups are number sets with plus and times, right? If that's what you thought a group was, you'd walk away from this with a very distorted and impoverished concept of what groups really are. So I feel compelled, just for your edification, to give you a very different example of a group, although this example will not actually serve any purpose that I can currently think of in the rest of this course. But this is just so that you get a better sense of what else can come up in group theory. And so what we're going to look at here is an example of a function space. So this is going to be a certain kind of a set of functions. That's a function space. So let X be any non-empty set. And then what we're going to do is form the set of all functions which have domain X and range X. So that's what this set X superscript X notation that you see here, that's what that means, is it's the set of all functions from X to X. But in particular, G, right, G is going to be the set that defines our group. G is going to be the set of all bijections taken from there. So that's made a little bit more explicit at the bottom here, where we write that G is equal to the set of all f in X to the X such that f is bijective. Okay, so I've told you what the set is going to be for this example. I next need to tell you what the operation is going to be. So the star, the operation on G, is going to be, well, how am I going to put two functions together? Well, the answer is that I'm going to compose them together. And this should again be familiar from previous classes, but let's just be explicit about this. So when I take f compose g, right, that's my operation, putting some two functions together in this example. Let's say that the result is this function h, which also goes from x to x, right? And that is something you can check. But the definition of this h is going to be given by this centered equation, which says h of x equals f of g of x for all x in big X. And so that is just what defines the composition of some two functions, and that is how we are putting functions together in this example. Now, I claim that with composition, we have an operation. That is to say, if you give me some two f and g in big G, then their composition is also in big G. Now, to check that, you have to notice that the composition f compose G is a function from x to x, right? That's part of what it is to be in big G. Also, you have to check that it's a bijection, because that's the other defining property of big G here. And this is, again, something that should be familiar from discrete mathematics, but it is, in fact, true that when you compose together two bijections, the result is a bijection. So anyway, that confirms my claim that this operation is, in fact, an operation. And so let's move on to the other things that we need to check to see that this is an example of a group. And the first thing we're going to do, actually, before I get to this, I should just mention that function composition is always associative. And that's not even special to this particular example, right? Any function composition, that is always an associative operation. Again, that is another thing that should be familiar from discrete mathematics, so I won't prove it here. But that confirms that other property that we need in order to have a group. So check, we know that this is an associative operation. And now we need to find the identity element. Now keep in mind the element is itself going to be a function, so I need to tell you what function that's going to be. And this function is often written as iota, that little Greek letter that looks like an I without the dot. And it is commonly called the identity function. And here's what it is, right? Iota of x is equal to x, right? You feed in any x, and it simply gives that x in return back out. So that's the identity function, and I claim that it is the identity element for this operation, which you are invited to check if you write down any function f, compose it with iota, and then input x. What do you get? You should be able to check that the result is the same thing as f of x. And you should also check that you get the same thing if you did it the other way around. So if you wrote iota compose f, that would be the same function as just regular f. And you check that again by plugging in an arbitrary x and sort of computing what the result is in both cases and see that you get the same thing. And finally, we should observe that this is a bijection, right? Because we need to know that this iota, this identity element, is an element in G, which means it needs to be a function from x to x, which it clearly is. It also needs to be a bijection, and it is easy to confirm that in this example, iota is a bijection, so it is in G. And now that we know that it has an identity element, we need to find the inverse of any given element. And that is where it is important that we said that G is the set of bijective functions, because it is exactly the bijective functions that are going to have inverse functions. And so you should note that for any given f, its inverse also goes from x to x, right? Remember that these need to be functions from x to x, and the inverse function will be that. It will exist because f is bijective. Again, that should be familiar from discrete mathematics. And you should be able to easily check that f composed with its inverse is equal to iota. And that concludes the check that this is in fact a group, that the bijective functions in x to the x is a group under the operation of composition. And that concludes the exposition part of this video. So now let's state a few exercises, and in the next video I will show my solution to these. The first exercise is to show that the set of all real 2x2 matrices is a group under addition. Take it that all the terms there are fairly clear and understood. Next, show that the same set under the operation of multiplication is not a group. Then show that if you take the set of all real 2x2 invertible matrices, that is a group under multiplication. And finally, we'll have one more exercise, and here you'll have an abstract but very small group, or, well, example. So the set X is the set of A and B, but you don't know anything about A and you don't know anything about B. It's abstract. And I'm going to give you this operation star. It is going to be defined by these four equations. So these four equations tell you everything about the operation star. And your task is to show that this is an example of a group. Now, some of this is going to be so trivial that it barely needs mentioning. Like for instance, x is non-empty, well, we can just look at it and see that it has these two distinct elements. The operation is truly an operation, not just a function. Well, right, it's displayed obviously, right? All of the inputs are all of the pairs of elements from x, and the output is always in x. So you can go ahead and write that down, but that is definitely the easy part. This does get tedious and obnoxious when it comes to showing associativity. But I do recommend that you really do it, right? Even though it's kind of a long and tedious process to show that this is an associative operation, I think it's probably a good exercise for anybody new to this subject. And I'm going to give you a little bit of guidance on exactly how the check for associativity should go. Now let's start by considering A star, A star, A. Now there are two ways that you could write parentheses for that. So you can see on the left that we have A star and then paren A star A. On the right, we have paren A star A, close paren star A. Now, associativity just means that you need these two to be equal. So you should compute both sides of this equation and show that it comes out the same. But of course, that's not the only thing that you have to check to show associativity. That is just the check when the triple is AAA. You'll next need to write down A star paren A star B. And again, shift the parentheses and check that these two things come out equal. And this is the check for AAB, and so continuing in the same sort of pattern, you'll need to write down every possible triple. Now that may sound daunting, but you do just have an A or B. So that's two possibilities in each of these three positions. That means that there are 2 to the 3 triples, that is to say 8 triples, meaning that you have to check 8 equations. It could be way worse. So I really do encourage you to go ahead and do the confirmation. And I've written down the first 4 equations for you right here. Notice that these are all of the equations that start with A. So if you were to basically write this exact same thing down, but instead of starting with A, it starts with B, that would get you all of the 8 equations that you need to check. So anyway, there you have it. We've already talked through non-empty, operation, associative. What's left after that is that you have to find an identity element. So just say which one, either A or B, is the identity for this operation. And then finally, find the inverse for each element. So find the inverse of A and find the inverse of B. And once you've done all of that, you'll have shown that this is an example of a group. And finally, I just want to close out by giving an invitation to ask questions. So if there's anything in the book or in this video that you are confused about, please leave a question in the comments, and I'll see you in the next video.